Hi there and welcome from Ventura, California to today's webinar, How the Latest RTK Inertial Technology Enables Accessible and Reliable Centimetric Navigation, sponsored by Inside GNSS, Inside Unmanned Systems, and SBG Systems. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders as today's webinar focuses on how high-performance real-time positioning in robotics, UAV survey, photogrammetry, and intelligent vehicles is now possible with entry-level inertial and GNSS products. Now, we've invited you along with over 500 professionals from 64 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher Inside GNSS and Inside Unmanned Systems, would like to take a moment to welcome you and introduce our main moderator for today's session. So over to you, Richard.
Thank you, Lori. Appreciate that. Welcome all from around the world. On behalf of Inside GNSS, Inside Unmanned Systems, and today's sponsor, SBG Systems, I extend a very warm welcome to our audience from around the world for today's webinar. We really appreciate your participation, and we're delighted you're with us. Now, I'd like to introduce our moderator for today's webinar. It's Alan Cameron. He's the editor-in-chief of Inside GNSS Magazine and the PNT editor for Inside Unmanned Systems Magazine. And as many of you know, he has covered the GNSS, PNT, and autonomous industries and research communities as both a writer and an editor since 2000, focusing on technical issues around continuous, reliable positioning and navigation. Alan, please.
Thank you, Richard. Thank you, Lori. And welcome to everyone around the world. I see we have boy, this is a robust attendance. Yes, so we have a large audience to perform for, gentlemen and ladies. We're going to get underway. Lori has just given you a mouthful of all the territory we're going to cover in this webinar. It is quite extensive, so I'm going to dispense with any further remarks and just get going. We're going to hear from Alexis Kinasha from SBG Systems, Märten Ström from U-blox, and Raphael Siriani, also from SBG Systems. Before we hear from them, Lori, let's hear a little bit from the audience.
Let's do that. On the screen is the first poll for today, and we would like to hear from each of you. In what sector are you most interested in applying inertial GNSS solutions? And we'd like you to go ahead and select one of the following responses: unmanned survey, UAV or UAS, defense military, autonomous ground vehicles, on-road, industrial robots, precision agriculture, off-road, or marine. Okay, well, we're seeing 32% unmanned survey, 10% defense military, 27% autonomous ground vehicles on-road, 19% saying industrial robots, precision agriculture off-road, and 12% marine. Any thoughts here, Alan?
Well, it's a very healthy representation across sectors. Of course, in almost any combination of integration, I should say, of inertial and GNSS in the world today, unmanned survey is going to be a leading concern, a leading pursuit. But we have good representation of the other sectors, of course, autonomous ground vehicles in a prominent position, and good representation, industrial robots and other off-road applications, as well as defense and marine. So a very diverse audience, just the kind we love to see. Let's get going with our first panelist. Alexis Kinasha is the Chief Technology Officer and co-founder of SBG Systems, a supplier of miniature high-performance inertial navigation systems. He holds a master's degree in embedded systems from École Centrale d'Électronique, and for the past decade, he has led the development of cutting-edge navigation algorithms and hardware, including attitude and heading reference systems, inertial measurement units, inertial navigation systems with embedded GPS, and more at SBG Systems. Alexis, please go ahead.
Thank you, Alan. So this first presentation will focus on the new markets that are enabled by affordable and robust RTK technology. We are first of all going to introduce very briefly our company, SBG Systems. We will also show all the applications where precision and robustness matters. We will then dive into our technology expertise, and then I will conclude my presentation by analyzing very deeply all the performance that our products can deliver. But first, SBG Systems is a leading supplier of orientation and navigation systems based on inertial sensors and GNSS technology. We are headquartered in France, near Paris, and we have an international presence. We have also a worldwide customer base and more than 25,000 sensors on the field. Now, when we talk about very high precision and high robustness, we can see that those words are very, very well suited for many applications. Of course, we can think about autonomous vehicles, but we can also consider ground robots, unmanned racing, industrial automation, many airborne applications as well, and also all the survey industry that's becoming very interested in the UAV mapping. Let's now see how we can deliver this very precise and robust navigation. Most of you might be familiar with the INS and the Kalman filter technology that is at the core of most of the inertial navigation systems. You've got on one end an IMU, which consists in accelerometers and gyroscopes that are integrated over time to obtain a very precise position and attitude in the short term. And on the other side, you've got aiding sensors like odometer, magnetometer, GNSS, and many other third-party sensors. These sensors are fused with the IMU and INS using an extended Kalman filter to stabilize the position, the velocity, and the attitude that might drift over time if you are only considering the IMU. However, it's very important to remind that using an EKF is not magic. If you want to have a robust navigation solution, you need to have still a good IMU. You need also to have a good external sensor, like a good GNSS receiver. But finally, you also need some layer of fault detection and exclusion. It's important to remind that even the best GNSS receiver will still struggle in very difficult environments to provide an optimal navigation solution. So it's important to have this layer of fault measurement exclusion. It's important to say that this is not part of the traditional Kalman filter. This is something that we need to develop on our own, and we have such technology at SBG Systems. Now let's talk about the IMU. I mentioned it is really important, and at SBG we are really proud of the expertise that we developed. All the IMUs that we deliver are calibrated over the full temperature range from -40 to +85 degrees Celsius. So this calibration is based on a very, very high-end calibration procedure using multi-axis rotary tables and temperature chambers. This enables very, very high performance in all the environmental conditions. All our sensor parameters are calibrated individually over the full temperature range, and we deliver a specific calibration report that shows you all the parameters of this calibration. Also, we want to make sure that if you have qualified our sensor during your prototyping phase, you will be also happy during your production for all the products that you will purchase. And we have developed a very specific screening process during our production to make sure that all our products are within a very specified performance grade. So if we have one sensor that do not meet the specification, we will manage to not deliver it, and we will just throw it away to make sure that all the sensors behave exactly the same way. And finally, we want to make sure that our sensors behave exactly the same way over the full lifetime. So we select industrial grade sensors only, either using ceramic package or very specific integration on our side, using a very specific in-house qualification process to make sure that we maintain the full performance over lifetime with no significant drifts or whatever. Now, regarding the GNSS technology, it's important to show that the traditional entry-level GNSS receiver up to now were only featuring a single band design, while on the other side you had survey-grade GNSS technology that was multi-band, multi-frequency. And now we have a new generation of GNSS receivers that delivers multi-band, multi-constellations tracking. And I want to highlight how this impacts the navigation. So having many signals in hands enables a better multipath and anti-jamming and spoofing resilience. It gives also more signals to correct some atmospheric errors. And also it enables very high accuracy like RTK positioning using almost instantaneous RTK fix. And it also enables instantaneous dual antenna heading computation. While using a single band design, you would need minutes of convergence time in a fully open sky environment. Using a multi-band design, you are able to achieve this performance level within a very few seconds. So it enables this high performance in the most challenging conditions. Very briefly, I wanted also to present the RTK technology that enables this centimeter navigation performance. So basically, this algorithm uses the GNSS phase and range measurement from two receivers. One is a base station that is stationary. It can be either user base station or a course base station or network base station, whatever. And you have, of course, your rover GNSS receiver that you want to measure the position. Of course, you will need a communication link between the base station and the rover in real time. But what if you want to increase even more the performance? There is a possibility by using a post-processing scenario. If your application is not requiring to get the navigation outputs in real time, you can benefit from a post-processing algorithm. So at SBG Systems, we developed a tightly coupled GNSS INS technology in a post-processing scenario. So the tightly coupled way will optimize drastically the robustness, especially in the most challenging conditions, because we are able to reject each satellite individually by making use of both inertial and GNSS data at the same time. And also we are working in a forward and backward processing. So one processing starts from the beginning of the log and one processing starts from the end of the log. And then we merge those two processings together. So in the graph here, you see the typical position drift that we could see in a forward processing for the blue trace and in a backward processing in the red trace. And the yellow trace shows the typical post-processed behavior. So this is an illustration showing how behave the merge processing when compared to the forward or backward processing. So it drastically reduces the position errors, and it also greatly improves the heading performance, especially when you are operating in long straight lines, for instance. Now, how to increase even more the RTK capability. So it's important to say that the RTK processing typically is able to cope with, let's say, 20 kilometer baseline. And if you have access to base stations around the rover, many base stations, but that are further away from the rover, it's possible to map all the atmospheric errors. So we developed a very specific virtual base station algorithm that is able to map all the atmospheric errors around the rover and to keep the centimeter precision accuracy while keeping also an RTK-like convergence time, so no convergence time on the rover side. So that's a key algorithm that we developed also to extend the post-processing kinematic performance. Finally, I want also to show very briefly how we can cope with the different heading challenges. So depending on the applications, you might have to cope with low dynamics or difficult magnetic conditions. And we have different types of products that can answer to these requirements. We see that using a dual antenna INS solution might help to solve most of these challenges. All these technologies are now integrated in the new Ellipse series, which is a very, very compact but high performance inertial navigation system, including a multi-frequency U-blox GNSS receiver on the Ellipse N and Ellipse D, also capable of doing RTK and post-processing as well. We even have a smaller design for those who want to integrate very tightly the product into their system. We have an OEM version that is probably the smallest multi-frequency INS GNSS integration on the market. Now let's talk a bit more on the performance. We made a lot of tests on this Ellipse series. Here we installed our sensors in a test vehicle that we have on our facility. We have a reference unit that is running a very high-end inertial navigation system, a quad-band GNSS receiver that is also post-processed to get the optimal performance. In this test scenario, there was no odometer installed, but we can even use an odometer to improve the performance. So we tested in a first typical launch scenario where we had, let's say, medium urban environment, some open sky environment, but all in all it was a good RTK setup. And we can see that the Ellipse D always provided less than 1 centimeter RMS on the position. On the roll and pitch, we were also much better than what we specify. And also on the yaw angle, we were below 0.13 degrees RMS. So we processed the Ellipse in 2 different ways. The first mode was the automotive mode, which takes advantage of the automotive constraints. And the other mode was the airborne processing mode, which would be more suitable if you have any vehicle that has no likely direction of travel, so like a UAV, an airplane, or whatever. So it reflects the performance that you will have also on an airborne application. But we can see that here we didn't stress enough the system to really see the performance. So that's why we tried to run the same system in a more difficult scenario with a much more tunnels, GNSS outages, medium to harsh urban environment with a lot of multipath, and still we exceeded the roll and pitch specifications. For the yaw, it was also very, very excellent, less than 0.2 degree RMS on the automotive, less than 0.25 on the airborne motion profile, and on the 2D position also we were less than 3 centimeter RMS. That's very excellent given the challenges that we have to face during this scenario. We can see the benefit of using the automotive motion profile compared to the airborne, especially during the tunnels and GNSS outages. And now I wanted to show you how we can even improve the performance using a post-processing tool. So here I just compare the automotive real-time operation with the same motion profile, but in post-processing. So on the roll and pitch, it's rather similar because we were already excellent in real time. But on the yaw angle, we could reduce significantly the error down to 0.1 degree RMS. And on the 2D position, we could reach 100% of the time under 10 centimeters, even during the tunnels, and with no odometer, so it would even be improved using an odometer. And 99.7% of the time we were below 5.8 centimeter of error. So to sum up, the post-processing drastically improves heading performance, and it maximizes the position accuracy during the most challenging conditions. And finally, to conclude my presentation, I wanted also to highlight the benefits of using a multi-constellation integration. So here I just look at the RTK fix rate, which shows the maximum performance. When the RTK is fixed, it's much more precise than using a float solution. So having more fixed epochs is always a better thing. So we can see in this very challenging condition, using a full constellations, GPS, GLONASS, Galileo, Beidou, 76.9% of the time we were in PPK fixed. And as we drop some constellations, we somewhat reduce the fixed rate down to 67.8% in GPS and GLONASS only, and only 49% in GPS only. So as you see, having more constellation is always a good idea, and that's why at SBG Systems, all the constellations are always included in standard. There is no extra cost or no options to add further constellations or further signals, because we really think that it's important to have all the signals in hands. And that concludes my presentation. Back to you, Alain.
Thank you, Alexis. For those in the audience, if your interest was piqued, as I'm sure it was, by the PPK software, we have the mention of it and the explanation of it. We have a full-on live demo of it coming up later in the webinar. Now we turn to Märten Ström from U-blox. Märten is Director of Product Line Management of Industrial Navigation and Robotics at U-blox. U-blox, of course, is a provider of wireless and positioning modules and chips for the automotive, industrial, and consumer markets. Märten focuses on high-precision GNSS products and business development. He holds a master's degree in applied mathematics, computer science, and physics from Abo Akademi University. Märten, floor is yours.
Thank you, Alan. And thank you all for being here with us today. Yes, my presentation is going to be split into two parts, where I will try to be brief in this first part, providing a bit of background before I go into the second part and show more hands-on, I hope, illustrative examples of what you can expect out of RTK in various environments. To give a bit of background of U-blox and who we serve, we've been doing GNSS receivers for some 20 plus years, and it's probably for these products that you know us the best. But please let me point out also we do cellular and short range products to see here, a few displayed. And back to the GNSS receivers, proud to be able to say that we shipped our 500 millionth receiver last year. And we serve 3 core markets illustrated here by the steering wheel being automotive, the robotic arm, the industrial market, and the sport watch being illustrating the consumer markets, and some 7,000 plus customers around the world. And you know, while serving such a large and broad spectrum of customers, we come to observe a few trends. And here today we focus on the trends toward automation and towards high precision GNSS. So throughout the years for GNSS to be competitive, you see a number of KPIs, a few of them depicted here. The first one here on the far left, best accuracy, will of course always be with us. Accuracy is addictive, we say, and providing the accurate position is what GNSS is all about. And of course we want this to be as good as possible. However, for a growing number of applications, and with this trend towards automation that I mentioned, improved accuracy in a reliable way is not only nice to have, but it's absolutely essential and at the core of a growing number of applications for them to be able to operate. And with this in mind, based on this trend and recognizing these growing number of applications, we shaped this vision to make centimeter level accurate navigation available to everybody. I mean, with this, we mean that we'll try to take this technology, RTK, and break out of its niche markets where it has existed for years, decades, and we embed this technology, RTK technology, in a small form factor, in a power efficient small module with a price level that can do just that, like expand into new areas and still provide these high level navigation in real time, and see where it can take us. And for this, as part of this journey, for this to be robust, we also brought in the element of multiband GNSS in our products with this same thinking. So we now have multiband receivers available for automotive applications, for timing industry, and for this high-end navigation that we talk about here today. This step, single band to multiband, was indeed a big part of this, and I'll show you some examples of this in the second part then. Applications, I only have this simple sketch of what volumes applications we see and imagine, or already see, I should say. Of course, when we started this journey, we anticipated a number of customers and markets that would pick it up. And this has played out pretty much as anticipated, with a very positive uptake on the market. It's inspiring to do this and be part of this, to serve a broad range of applications. And the product and technology is really there, you know. It's groundbreaking in a way that it enables customers to broaden their offering and enter new markets. And it can even see that it enables new applications, and maybe even application that we didn't anticipate. The robotic industry puts out machinery, big and small, that it's inspiring to watch. And you know, the UAV light show that you saw at Super Bowl, some of you might have seen that could be one example of an application I don't dare say we saw coming. So fun and inspiring, but with this short intro, I'll end this first part and give the word back to you for a while, Alan.
Thank you, Märten. We have time for a couple of questions for our panelists. We're going to go back to Alexis with a few questions, then we'll proceed with the rest of Morten's presentation. Alexis, are you using a loosely or tightly coupled INS plus GNSS algorithm?
That's a good question. So basically, we developed both loosely coupled and tightly coupled GNSS integrations, and depending on the product, we will use one or the other. So on Kinasha post-processing, definitely we are using the tightly coupled, which is which provides the best performance. We have also high-performance inertial navigation systems that are which hardware is capable of doing some tight coupling. On the Ellipse series itself, we have a smaller CPU that is running a loosely coupled integration. Still, it delivers a very good performance level with the U-blox RTK capability.
And one more for you, Alexis. You've obviously partnered with U-blox on some projects. How do you compare the U-blox GNSS performance with traditional survey-grade receivers?
Oh, that's an excellent question. So I would say that traditionally all the RTK, all the survey industry was really familiar with the survey grade receiver manufacturers, and they give excellent performance even in the most challenging conditions. And U-blox was more ranging for more entry-level applications. But now what we see is that with this new multi-frequency GNSS receiver from U-blox, we can get very, very good performance level, even in challenging conditions. And the difference in terms of performance becomes really, really difficult to observe in this, even in challenging conditions.
Accuracy improving constantly on all fronts. We will have time for more questions following 1.5 more presentations. So I encourage everyone in the audience to use your interface panel to submit questions for these experts. Before we go back to Morten, Lori, let's canvass the audience one more time.
Okay. On your screens is our second poll for today. And the question is, what challenging conditions do you have to face the most? And again, go ahead and select one response: long straight lines, low dynamics, urban canyon, multipath environments, GNSS outages, or jamming and spoofing. Okay, looks like 16% coming in with long straight lines, low dynamics, 48% urban canyon, multipath environments, 23% GNSS outages, and 14% jamming, spoofing. So, Alan, what are your thoughts here?
Well, Lori, I am both surprised and unsurprised by two different results here. I'm not surprised by the most common challenging condition, urban canyons and multipath environments. That's a key preoccupation in any kind of consumer or industrial application, which would cover a large swath of the market. I am surprised that jamming and spoofing is such a low challenge. Jamming and spoofing is taking up a lot of attention in R&D circles around the world, and it is a coming threat. But apparently it's not one that's faced by our audience, or at least not quite so much. Our panelists may have thoughts to contribute on this later, but for now, let's go back to Morten's presentation and get a little bit closer in on RTK and centimeter level navigation.
Yes, thank you for that. Yeah, back to this vision to have the centimeter level navigation available in all environments in a reliable way. There's a lot to this, and I can only scratch the very surface of it, highlight a few building blocks and the impact they have here in the slides to come. More precisely, I tried to show you that the challenge is just that, to provide the centimeter level navigation itself is only part of the challenge, arguably not even the most difficult part, but the challenge is really to do this reliably, continuously in all kinds of environment. Our customers always push us towards the most difficult environments, and honestly have no understanding or very limited understanding of any limitation there might be in multipath, which many of you highlighted there as a big challenge for all of us. But so I'll show you a few examples here. I'll start in a very open environment. In an open environment like this, you can expect that the receiver has the luxury of working with signals that are not affected by multipath. We can expect continuous carrier phase locking and something that the RTK algorithms need, and basically just a very friendly environment. Good low-level measurements for us to work with. And I'll show you these results here, comparing single band to multiband RTK to highlight a few points. You could think here now that getting higher accuracy is not the reason why you go for multiband, if you understand me the right way. Under certain circumstances like here, if we operate in very open environment, you can get the same accuracy with the single band receiver. But if you consider a single band solution, it's very important that you know and are aware of the limitation. As soon as you start to stress that kind of system, you will experience some symptoms. And you can stress the symptoms not only by bringing it into the more difficult environment, but we could also have aspects of the dynamics of the applications, what kind of antenna you are using, are you starting to compromise the antenna, etc. So we recommend single band RTK only for the most cost-sensitive applications operating in the very open environment. That could be some UAV applications. I also here on this slide used the 95 percentile position accuracy to highlight a bit where I'm going with this. Challenge, as I said, not so much reaching the centimeter, but rather make it reliable, and how reliable we can provide that to the end application in all kinds of environments. So we go to more the environment where which maybe for many applications is a more realistic one, and this one goes then into the urban environments. It's not the most difficult urban environment, but still, and we must in these kind of environments then expect we will pass on the bridges, we will have a signal blockage, we will have a lot of multipath, and the challenges will be thrown at us. I still then compare single band to multiband. On the left side here you see single band, and on the right side you see multiband. I've not picked the worst and not the best. I just picked one example out of the hundreds of tests that we have done here, and pick this one to illustrate what you typically could expect. And I also choose to depict the altitude error, which is the largest error. It's larger than the horizontal, just again to highlight how it behaves. You can see on the left side on the single band RTK that in this kind of environment now, that with the multipath, with continuous signal outages, single band RTK will struggle. Sure, if we would have only put like the 50% value or something, it could have looked good, but you can see here that if anybody wants to automate things here, it's going to be a bit difficult. When we lose the centimeter level accuracy here, then it can take minutes for the receiver to get back to the best accuracies. And on the right side where you see the multiband RTK real-time performance, again, sure, with RTK you must always expect some glitches. When we pass on the bridge, for sure you will lose the carrier phase locked signals. and your accuracy will drop to some extent. However, with the multiband RTK, these events are like on the picture. They are quite different in nature. They are short-lived, and typically what happens is then when you come out on the other side of the bridge, we lock back and again are back to a very accurate position. The point being that depending on how far into the urban canyon you go, at some point it will break, and multiband much short-lived outtakes, and we do a quick reconverge, but if your application requires you can also of course take these out. You can imagine now by just looking at the picture that you can bridge these events with the help of sensors. And of course, it would be much easier to bridge the right-hand side, the multiband RTK with sensor than the alternative. So move a bit further. This is actually the last example. I could have maybe had more example with more time, but okay. Here we go we go under the thick trees, as thick as they come, and look at how a robotic application performs in this kind of environment. On this slide then you see the performance of real-time RTK aided by sensors. I could have brought a more difficult environment, similar like this, but adding the element of buildings on the side to also have blockage and multipath. Yeah, in these kinds of environments, RTK will work, but to reach the best or to bulletproof the availability, you need to turn to sensors to help. Sensor integration will ensure the continuous, highly accurate, reliable position. And you can also take note that it also enables the higher update rate. The sensor will bump up the update rate. We can do 8 Hertz with 4 constellations, but okay, with sensors you can do more. Here I show a 99% value then with the help of sensor, 14 centimeters, 99% in this data set. Again, just a typical one. Yeah, that's kind of gives you the picture of what you can expect. So that is a quick scratch on the surface what some of the building blocks can do for you. You can see on this picture here that there are elements like antenna, very important one, correction service also, and combined the right way, sensors or not, can be needed to give your application the needed accuracy and availability of this high accuracy. I do then have one final slide here on a topic of looking a bit into the future. Or not actually the future. We do have this already introduced in the M10 platform that we released last week or announced last week. So protection level. All our GNSS products, they are outputting the accuracy estimate attached to the position in real time. And now to meet the needs of robotics and others, we expand on this by providing also protection level. And this is there to give like an upper bound for what the receiver estimates the error, maximum error can be at the moment, and we give this at a confidence level of 95%. And it differs from the position accuracy estimate, and that it focuses on this upper bound and taking more parameters into account than just the accuracy estimate of the normal output. It it will continuously fluctuate and react to the environment, as we will see on the next slide. Here I show performance then from the M10 platform. So this is the newly announced platform, but here we are talking now, please notice, a single band receiver. We are back to an L1 only receiver and not any RTK, but still, just to illustrate what we also then will introduce on the F9, the multi-band RTK products, I think first half next year. But on the single band, we see here now then the protection level here in blue reacting in a dynamic way to the environment and more, keeping this protection level staying under 5 meters for on this road test around Zurich for 95%. When we'll introduce this on an RTK product F9P, then next year we can expect this to go down a magnitude. So that's a small teaser for the future. And with this, I will close already now. I hope to then come back to answer questions in the closing section. I'll give the word back to the next speaker, and I welcome you to visit our website to read up on our products. You see M10 there, you see the protection level explained more in detail, and you see the ZF9P there presented, the RTK receiver that we talk so much about here in this presentation today. So thanks, and over to you, Alan.
Thank you, Märten, and we will indeed be coming back to you with questions after the next presentation. We're going to hear now from Raphael Siriani, Chief Software Architect and co-founder of SBG Systems. He has a master's degree in Embedded Systems Engineering from the École Centrale d'Électronique. In the inertial field since 2006, he is in charge of embedded firmware designs, hardware designs, and MEMS sensor tests, characterization, and calibration at SBG Systems. Raphael, I know you have a software demo for us. Please proceed.
Thank you, Han. So yeah, before I dive into the Kinasha demonstration itself, I would like to introduce Kinasha. So Kinasha is an in-house post-processing software we have been developing for the past 5 years now. And the idea is to be able to both analyze and optimize the real-time performance of a unit, as well as get the ultimate accuracy. So basically, as Alexis explained, post-processing will bring the much better heading information, as well as much better position information, especially in GNSS denied or GNSS harsh environments. And Kinasha is also a very interesting tool for both productivity when you have to process a lot of serving missions, but also for R&D and data analysis and to review if everything is going well for real-time products as well. And we do use Kinasha internally for a lot of evaluations, and I will share with you some insight on U-blox Ellipse D log to show how we can analyze the quality and all that stuff. Kinasha, we have several versions to best fit your needs, starting with a GNSS only option that basically compute any GNSS receiver in PPP, PPK modes, and we have specific processing modes such as the virtual base station that I will be showcasing later. Then we have a light mode for Ellipse only, and the idea is to provide a very cost-effective solution for Ellipse products from SBG. And finally, we have a UAV version and the Pro version. So the UAV one is also very price aggressive and is especially designed for UAV markets with some limitation on the trajectory scale size. And the Pro version is able to process any type of mission. Something very interesting with Kinasha is that the software, both our hardware, in fact, and our software such as Kinasha, are very open and interoperable with a lot of other manufacturers and file formats. And for instance, Kinasha is able to process directly binary data from Novatel, Trimble, U-blox, Septentrio. And for instance, on Septentrio and Novatel, we can directly also process the INS data as well, because Kinasha can process not only third-party GNSS manufacturers, but also third-party INS and IMU manufacturers. We also have CSV text files, RINEX and SBET format support to be able to accept any type of GNSS or IMU data, and SBET to be able to export to any type of third-party software. And I will also showcasing export solutions. So let's go ahead and let's see how we basically do a processing in Kinasha. It's mainly 4 steps: importing data, checking that everything is all right, such as the settings of the unit, then processing the data, doing a little bit of QC on the data, and finally we have to export the data. So let's fire up Kinasha, and I will start by creating a new project. So this is a UAV project that is a single antenna UAV project that has been recorded using a Quanta unit. So here I see the trajectory overview and data coverage. And I will just review that everything is okay, so I can see the trajectory here. And now Kinasha is automatically picking up all the nearby base stations and downloading the base station data. And as you can see in this specific situation, we are quite far from the base stations. And if I measure the distance, I am 40 kilometers away from this one, 30 kilometers roughly from this one, 70 kilometers from over base station. So in this situation, a short baseline is quite complicated because we are too far away from the base stations, but it's an ideal situation for virtual base station computation. So you can see that Kinasha has automatically picked up and suggested the best way to achieve a centimeter level accuracy, and has created a virtual base station network using these blue base stations. And you can see that the whole green area, in fact, will be with the VBS algorithm, you will be able to get the exact same accuracy and robustness as using a short baseline RTK computation. So now I will validate my network. So when we do the validation, in fact, we make sure that we have all the needed data, that we have adjusted the base station position and all that stuff. And in this case, I see that my base station, this one here, has not the correct published position. And Kinasha has run, in fact, automatically a static PPP computation on the base station to make sure that the base station is correctly located. And I see that I have a mismatch. So I will just say, okay, use the PPP computed position for this master base station. All the other base stations position will be automatically adjusted by the algorithm in respect to the master base station, and your trajectory will be located in respect to the master base station. So now let's go ahead. Everything seems to be okay. I can move forward, and in fact I'm just reviewing the settings as all the settings have been read directly from the unit, such as the GNSS lever arms. So you see here that it's a single antenna application, and I will now have the trajectory preview, and I will run directly a tightly coupling computation. So it's a 20 minutes long log, and you will see that the computation is very, very fast. You can see in real time the data coming in, and you see that for 20 minutes of UAV log in this situation, we will need just a few seconds to do both the forward, backward, and merge processing. And we are running 3 paces in forward and backward to further improve heading accuracy and positioning accuracy especially. So in this situation, I can also assess some quality information, and I can see that I have a 100% at PPK, so RTK fixed solution. I have quite nice road and pitch information, 0.04 and almost 0.01 degree on the estimated accuracy. But I can also review the separation. So the separation is the discrepancy between the forward and the backward computation. And you see that it's even better. I have 0.1 on the heading. So the heading is very accurate in this type of log. So it's typical UAV log, single antenna. We see a very nice heading and stable heading here. And on the position itself, 2 centimeters on horizontal and 3.3 centimeters. And also you have to look at the maximum error because it's also very important. You see that in this specific, typical UAV application, you are always well below what you need to do a very accurate survey mission. The separation 1.5 centimeters, just amazing. You have to keep in mind that this is not the ideal situation because in this case, we only have base stations that are quite poor. In fact, it's a GPS only. It's 30 seconds base station data rate, so it's clearly not the ideal situation for VBS. And we can also see some nice reports to show that. And we can see here that on the VBS, we have all the VBS report here. And you see that, for instance, this base station gray is not valid because we can't fix it. It's because we have a lot of missing data and jumps on the signal because this base station is just crappy, in fact. So you see that the software still do a very nice job even in this difficult situation. You can review a lot of different metrics such as having altitude, quality control. We can see the gyroscope bias. We can see accelerometer's bias, for instance, very, very stable. We can see the error angle separation between the forward and the backward. So yeah, you have a lot of different metrics to review the data quality. So now, in this specific log, the user also had a U-blox based base station. It was an Emilide base station, in fact. And I will just show you how easy it is to import a U-blox base station. So it's directly the U-blox binary file that we are drag and dropping to Kinasha. And we directly read the binary files within Kinasha. And it's very important for us because most converters you could find to convert binary U-blox to RENEX tends to decrease the data accuracy by introducing some errors. So it's very, very nice to have a direct binary support for U-blox. So I have imported the data, and now you see that I don't know the exact position of this base station. It's just a standalone position, not accurate enough for my mission. So I will just set up the antenna because I didn't set it up and compute a static PPP on this base station to get the exact base station position. I get the PPP1. It's bare than 1 centimeter accuracy. And now I will just let Kinasha pick up the best solution to achieve the optimal post-process solution. Of course, in this case, Kinasha has picked up the base station that is just near the trajectory instead of the virtual base station, as you can see here. And now I'm just going further, and I will trigger just PK computation only. So it's a GNSS only computation, just for this demonstration. And you see we have all of the trajectory that has been computed. In yellow, you see the original PVT from the GNSS. I will remove it. And you see here in green, I will change my display. You see in green here the computed GNSS solution. And if we look at the accuracy, you see that it's 100% fixed solution as well. Finally, let's talk about, I will trigger a tightly coupled processing. And now I will show you also how we can export the data out of Kinasha, and you will see how easy it is. We support several files formats such as SBET, ASCII, Google Earth, and all that stuff. And of course, you can also export the data based on a distance on a specific event time. So if you're, for instance, recording some photos or anything based on a shutter event, we log the shutter event in our product, and you can export the data on this specific shutter event. So in this case, let's go ahead and see what we can do. Have a photogrammetry here, export profile, and I can set up all the parameters, such as where I would like to export the data, if I would like to export all epochs or on an event based. And I see that I have 95 events C. That is, in fact, for each picture that has been taken during this log. And then I can create exactly which file format I would like by just drag and dropping some data. I can say, okay, I would like the accuracy, roll and pitch accuracy. I just drag and drop. I can even change the sign and all the stuff quite easily and proceed. And I'm done. Exported data. Okay. So I hope I still have some time, just a few minutes, to show you on a typical Ellipse D urban environment what post-processing can bring and what Kinasha can also bring to assess and analyze the data. So here I will just pick up some specific areas such as this one. And here you can see in the green line is the post-process solution, the yellow line is the U-blox real-time solution that has RTK reception. And you can see clearly here, for instance, we have RTK on the GNSS itself, but here we have RTK float because we have a huge bridge with a lot of metallic parts and very difficult for the GNSS. And you see in this type of situation how the INS and how the post-processing can improve a solution, and I can play it. So it's a quite interesting way to also see how things are going. And you see here the GNSS here and the INS here with an associated quality indication. It's an ellipse, in fact. And you see the GNSS starting to go crazy because we have the bridge and then reconverging. But on the INS side, you see that it's perfectly fine. And if I look at the position type information instead of the position accuracy, you see here that the INS has using velocity constraint because we don't have any GNSS reception here. Here we are in green RTK fixed solution. Here we have RTK fixed solution and RTK float here. And you see that on this whole area, the tightly coupled post-process solution was able to provide RTK fixes, but for a real-time U-blox, you got RTK float solution that is perfectly fine for a real-time GNSS, considering how harsh these bridges are. And we have tried a lot of GNSS receivers under those bridges because it's always very difficult for them. So I hope you've got a better idea of what Kinasha can bring to you, both to post-process and get the best accuracy, and also to assess the data quality and assess the real-time solution of an ellipse or any INS or GNSS. Thank you very much, and back to you, Alan.
Thank you, Raphael. We are going to show you a slide of resources. If you have questions about any of the presentations you've seen, we're going to go to some of the questions that have been submitted during the webinar in just a minute or two. Right now, there are some contact points for SBG systems. And then, Lori, let's have our third poll on audience preferences.
Okay, yes, third poll on the screen here. And again, we'd love to hear from each of you. What is the most driving factor in your navigation system selection? And options here are accuracy, robustness, integrity, navigation ability, price. Okay, we have 42% accuracy, 31% robustness integrity, 11% with navigation availability, and 16% coming in with price. Alan, any thoughts here?
Well, I don't think I've ever seen a survey where accuracy was not the leading answer among choices of this nature. Of course, accuracy is what PNT is all about. But it's nice to see that increasing attention is being paid to robustness and integrity as PNT is used in more and more applications. The importance of safety only goes up. And so robustness and integrity is reflected in that. It's nice to see that price, while a consideration, is not the leading one. I know in some other industries that we shall not name, price is the only driving factor, but that is not true in PNT and GNSS. We're going to turn now to audience questions. And just for our panelists, I'll preview you a bit. I'm going to go 2 by 2 through some of the questions that have been submitted. We're going to have 2 for Märten, 2 for Raphael, 2 for Alexis, and back again to Märten for 2, and then after that we'll freeform it. Once again, here are some resources for you to check for further information on both SPG systems and U-blox. Märten, can you say a few words about the antennas used in the RTK results that you showed?
Yeah, so that's a relevant question, right one to ask. We always try now these days to use small, affordable antennas suitable for the volume applications we are targeting. So in the urban test drive, we had this patch antenna placed on the car roof. So the car roof itself provides an excellent ground plane. In the robotic, there was also the same patch antenna, this time on a smaller ground plane. So this antenna is actually, its product name is NMB, and you can actually, it's the one we ship with our evaluation kit, and you can actually get it from our website, web shop as well. And in the walk test, I actually think there was a survey grade antenna, and I can tell you, yeah, if I would have put a Verse antenna there or a cheap patch L1 antenna, I think we would start to see already then the L1 RTK performance not reaching the multiband performance already in that open environment. If you go away from a survey grade antenna that was used in that example, yes. But we tend to use always use these kind of the new wave of antennas, small patch or helical antennas that we find, and only use the survey grade antennas for like reference for the truth systems. Yeah.
And yeah, when we're talking about multiband, Märten, there are several flavors of multiband, not just one. And at U-blox, you have options. You seem to support L1 and L2. Others have chosen to support L1 and L5. What do you have to say about this?
Okay. This is of course a question we are asked quite often. So let me start by pointing out that in this ZF9P today we support all the systems on L1 on the upper band, and on the lower L band we then pick GPS L2 obviously, but also then GLONASS L2, and we go down to the E5 on the L5 band and pick Galileo E5B there and the Beidou B2I. So that also then explains why I talked throughout about multiband and not dual band, because we are technically picking cherries there from both L2 and L5 and all the ones on L1. We did this because we wanted more signals. We prefer to have the bigger number of signals. We saw that gave the better performance than the option that would have been L1, L5, where there were not that many signals still a year or two ago. This is changing a bit. There's aggressive launching going on in China primarily. The others are not that fast, but there is a growing number of L5 signals, and sure, we recognize also this, and we will also have L1, L5 products out. We are looking for the RTK variants to become available, or there will be these products L1, L5 next year from us. But for most of us, I would still argue that for the ones that look for RTK solutions, L1, L2, this mix of the multiband that I explained, I still feel is the safe and good choice, reliable choice. We can then, when next year comes and we have even a few more L5 satellites, we can then put them side by side together and look together on how, what is the performance. There are indeed, there are reasons why you would be interested in the L5 GPS, particularly than being more modern than the L2 GPS signal. So let's put them on par next year together, and everybody can judge for themselves.
Yes, one thing we know, and excuse me, in PNT as in life, change is constant. L5 is coming, is not yet here, but next year, our answer, your answer, may be different. Turning now to Raphael, two questions for you, Raphael. First one, can I mix my own base station data with CORE's base stations in Kinasha to extend the RTK range?
So in Kinasha, we have 7,000 CORE's base station, and of course you can both use the CORE's base station alongside your own base station. So if you would like to create a huge virtual base station network for 500 kilometers, for instance, you can use CORE's base station and just place some base station of your own to improve this network. So yeah, of course you can combine both. And finally, very important also in Kinasha, you can use paid offline base station services as Kinasha support credentials inputs for base station access.
And again, referring to Kinasha, how is the master base station selected among the other base stations in a dynamic scenario?
So yeah, it's a really interesting question for virtual base station. So in fact, the master base station is the one used to actually compute the RTK, the PPK solution, and all the other base stations in the network will be used to evaluate, estimate, and compute atmospheric and ionospheric errors and all that stuff. So normally the master base station should be the best one. And the best one is not only the baseline that is taken into account, but also which constellations are available, if we have some cycle slips on the base station, the data quality and all this stuff. So we have a quite complex algorithm in Kinasha to pick up the best master base station and also to pick up over nearby base stations. And something also very interesting with the virtual base station algorithm, it's not only used to access RTK in remote situations, but it's also used to achieve corridor mapping applications. If you have a very long straight lines, 300 kilometers, for instance, you can have some base stations along this long straight line, and you will get all along the line short baseline RTK accuracy, so just 1-2 centimeter. And if you are interested about the specific use case, we can share some test results and some test data we have.
Fine. And do you have a, turning to Alexis now, or Alexis or Raphael, either one, at SPG, do you have a free service of the virtual corrections?
Yeah, I think this question is mostly referring to getting access to free correction data on the post-processing, and of course Kinasha is able to
to download automatically corrections that are available for free. So these are the 7,000 base stations over the world that we can download very easily and with no specific user action. Kinasha does it automatically.
And one listener is interested in using Ellipse N plus Kinasha on a drone and has a concern with the true heading capability after PPK. Is it enough using a single antenna for Ellipse N, or compared with Ellipse D dual antenna? And they say they're using the drone for survey and mapping purposes.
That's a very good question. So I would say that a single antenna system in a post-processing environment will be suitable for the most typical UAV survey conditions, since the post-processing will drastically improve the heading performance. Then even a single antenna system can operate very properly. But if you have to face with more challenging conditions like corridor mapping, as Raphael mentioned, if you have to run over very long straight lines, that's likely to be interesting to get a secondary antenna to improve the heading. In the demo that Raphael showed, that was a UAV survey, very typical UAV survey on a Quanta series, which provide very similar performance as the new Ellipse series in post-processing. And in that scenario, we were using only a single antenna setup. So I think it answers the question.
Thank you. Thank you. Märten, for RTK, you need correction services. What's the benefit of multiband if you don't have correction services?
Okay. So if you take out the correction services and just look at the multiband receiver, how it performs, then what you'll get. I think most of us then think of the position accuracy and the accuracy domain here, and what would that look like. And I guess it depends on what world you live in if you think that is then worth the money. I think I know. So in our data sheet, we specify then if you don't have any corrections, not even S-bus, we specify 1.5 meters circular error probability for these ZF9P and other multiband receivers of ours. And for the single band, it's been 2.5 meters, 2 meters. So is that half a meter worth the price? Not sure it always is. But if you then add the S-bus, you could be down to 1 meter in our data sheet, and I can even say that can sometimes come across as a bit conservative compared to what we can see in a real application. Also, there are benefits, as I said a bit in the previous comment, like the L5 of GPS is interesting, and it comes down to then the receiver to use the signals in the optimal way. In a heavy multipath environment, it would weigh and look more towards the L5 or towards the more modern signals, and in an open environment, it would stay to L1. So it can also be a bit depending on to what extent the receiver can really optimize this, but you wouldn't go much under 1 meter, regardless of how you tune it and how you work with it and what kind of applications. You would kind of stay on that level. So it's then down to the price level. Would your application feel that is important enough to carry the cost? I do think these multiband will find their way also to very cost-sensitive applications in time, and there could be other reasons beyond the accuracy argument why you would look at multiband receivers. It could be, for example, timing industry or any critical infrastructure that would turn to multiband for a security integrity aspect, as this multiband allows for cross-checking and raising the bar a bit in this race against spoofing and jamming and interference. So for that reason, I think timing, they would go for that reason often. Yeah.
All right, and another question for you, Märten. Do you use any dynamic model if no sensors are used?
Yeah, we do that. We do have dynamic models for all our products, and these would include automotive, pedestrian, static, and a few more airborne, different airborne models with different G-forces. So yes, absolutely. And the effect of these then is that they have different sanity checks on the solution. Primarily that, also in a way like put expectations on the G-forces and jerk that you can expect. So that's described in the product documentation, and you can see there, based on the dynamics of your application, what would be the right one for you. Yeah.
Turning back to Kinasha, Raphael, one listener wants to know, is it possible to receive a demo version of Kinasha? And also asks if INS data, for example, in an ASCII file from units that are not SBG units, could that be integrated?
So for the demo version, we do have some specific demonstration and evaluation version of Kinasha, but you will have to contact the sales team for this specific topic, of course. Regarding the ASCII file import, it's a standard in Kinasha to be able to read both JSON text file with all the INS settings, such as the GNSS lever arms and all that stuff, as well as ASCII CSV-like text files for IMU data. The only limitation is that you need to ensure that the IMU data are correctly time-stamped to UTC or GPS time, or Unix time. It doesn't matter. You just need to make sure that the IMU data are correctly time-stamped, so Kinasha can combine correctly the GNSS data and the IMU data during the post-processing. And we do have also some IMU models such as LN200, LITEF IMUs, Honeywell, any type of IMUs. So it's not too much complicated for us to handle this type of IMUs. So yeah, it's standard feature.
Terrific. Well, I'm going to thank all our panelists, Alexis, Märten, and Raphael. I want to thank SBG Systems for sponsoring the webinar. And I want to thank the audience from around the world for paying such rapt attention and for attending in such large numbers. This has been an Inside GNSS and Inside Unmanned Systems webinar, how the latest RTK and inertial technology enables accessible and reliable centimetric navigation. Thanks again for attending. Stay safe out there, everyone in the world. And you will receive, as Laurie is about to tell you, you will receive a follow-up containing a package of webinar materials, and also we encourage you to share that with your colleagues. Anyone who missed the webinar can still sign up on our registration page and have full access to all the audio and all the slides. This will live on. Thank you once again to the audience, and Laurie, back to you.
All right. Well, thank you, Alan, and most importantly, thank you all for joining us. This is Laurie Dearman saying, hope we see you on the next one. Bye for now.